We present a serially actuated soft robot consisting of 3 actuators separated by tunable passive valves. Actuators 1 and 3 form spirals when filled with fluid, which allow for anchoring into the wall of tube-like environments without blocking pulsatile flow. Actuator 2 extends when filled with fluid, allowing the robot to locomote when the valves are tuned correctly. The robot's valves are modeled as flow-restricting orifices, and the actuators are modeled as nonlinear, spring-loaded hydraulic accumulators. The locomotion sequence was split into critical stages A through G, with each actuator represented by a different color. Critical volumes were defined, where VI is the initial volume coefficient of the actuator, VC is the volume required for the spiral to make contact with the tube wall, and VF is the volume required for the spiral to anchor into the tube wall. For ideal locomotion, actuator 2 should not make contact until after actuator 1 is anchored, and actuator 3 should not begin its actuation until after actuator 2 is finished extending. This prevents tensile forces from developing on the tube wall and ensures that extension in actuator 2 is not wasted. A simulation and grid search was performed over a range of valve coefficients, and an objective function was then maximized to produce orifice coefficients that augmented the extension of the robot per input pressure cycle. Locomotion was achieved experimentally after connecting the robot to the following closed hydraulic circuit test bench. Locomotion was also achieved using a syringe to manually actuate the robot. We would like to thank the MinDrive Initiative and the National Science Foundation for supporting this work.